So Tim got his PhD at the University of Bonn, and he's now in his second year as a postdoc at the SCIP in Santa Cruz, and he's going to tell us about implications of LHC Higgs results for the MSSM.
Yes, thank you very much, Enyo, and thank you very much for inviting me. It's a pleasure to be here in Davis, and I'm trying to give you my perspective on how we can use LHC Higgs data and how we can use it to study beyond the standard model physics, and particularly I will focus on the Minimal Supersymmetric Standard Model. And although this is a quite well-known and studied model, I hope I can give you maybe some new ideas or new surprises or new features of this model which might surprise you. So, of course, this is a Higgs talk, so I should start with the Higgs discovery. As you probably all know, the LHC found this scalar boson with a mass of 125 GeV, and which nicely showed up in these two channels where the Higgs decays to Z bosons into 4 leptons, and we observe this as a resonance here in the invariant mass spectrum, and the same also in the diphoton channel. And thus far, all the studies of these coupling properties, spin, and the CP properties of this scalar boson are in very good agreement with the standard model hypothesis, and this has also led to the Nobel Prize Award being given to Engler and Higgs in 2013. So let's have a closer look at what the LHC actually measures. So this is a plot which contains all the different rate measurements by CMS in all the different decay modes, and also with specific tags to identify the production channels. And one has to really keep in mind that the LHC can only measure signal rates, which is a product of the cross-section, production cross-section times the branching ratio. And if you want to infer this information onto the couplings, you have to do additional model assumptions, because you cannot directly measure the total width of the Higgs boson. In the standard model, it's simply too small to see this experimentally at the LHC. So if you really want to study the coupling properties, what you usually do is to perform global fit to all this data and try to identify these kappa scale factors, which just scale the partial widths or cross-sections that are proportional to the relevant couplings of the Higgs. And so if you do this, you see this is the Atlas and CMS combination from last summer. And if you look at the precision, you see that at best we can reach some precision at the moment of the 10% level.
Can you remind me, I mean, there is this measurement of the width which is nowhere near the standard model level, but it is surprisingly, at least at several times the standard model level, right? Does that play any role in breaking any degeneracies at all in this fit? Does that measurement have any impact at all on this?
Well, so you measure off-shell Higgs to ZZ decay, for instance.
Yeah.
And you can infer that to derive a limit on the total width. And yeah, this breaks kind of the degeneracy, but it's an additional model assumption, because you really have to have some physics which, if you exact these features in the off-shell region, so you have the same scaling of the production mode and branching ratio in the on-shell and the off-shell region to obtain this limit. And if you have some new physics which doesn't do this job, then you're screwed.
But you're not including it in this?
I'm not including this at the moment here.
I wouldn't expect it to do much. I just questioned if there would be anything at all. That's my question. If you did include it in this, I mean, you could include it in this fit. Certainly the standard model is compatible with it, but some of your kappas that you consider may not be compatible with it.
Right. No, well, in this case, there's this assumption that there's simply no additional Higgs decays, so there's no additional contribution to the total width.
It's already put in a stronger way here.
Yeah, this is even stronger assumption, right? So this will be even more blown up the ranges here for these kappa scale factors if you take the Z. Okay. But what we are ultimately interested in is, of course, physics beyond the standard model, and this is very well motivated by, for instance, the hierarchy problem and the question whether there's a dynamical reason why we have more baryons and antibaryons in the universe, and also the nature of dark matter is still unknown, and all these problems cannot really be solved in the standard model. So if you look...
I'm sorry, I will let you do your talk, but can I ask one more thing about what I was asking about?
Yeah.
So the fact that when you show this fit for the kappas, that the fact that there aren't, that the range is pretty narrow around the standard model, is basically limited by total rate measurements, is that right? In other words, you can't have completely crazy value of the couplings because that would conflict with absolute rate measurements. Is that right? If you just had ratios, you would probably have some crazy... I'm asking, what prevents the kappas from sort of going without bound eventually?
So in this case, in general you can allow an additional Higgs decay to new physics, which suppresses all the standard model final state branching ratios, right? And at the same time, you can scale up all these kappa scale factors such that you increase the production nodes.
Right.
So there's a perfect degeneracy if you allow for that. If the branching ratio to new physics really goes to 100%. So there's no upper limit in this case on these kappa scale factors.
Okay, thanks for reminding me. Yeah, good.
Okay, so if you look at the landscape of beyond the standard model theories, which are on the market, then you often see that they have an extended Higgs sector with multiple charged and neutral scalars. So in these models, you generically expect deviations in the signal rates or coupling properties of this discovered Higgs boson, and in addition, you would also hope to see some additional Higgs states at the LHC. So in order to really study BSM physics with Higgs data, we need on the experimental side really precise measurements of these rates and the mass. And also we have to continue looking for additional Higgs states. On the theory side, at least in the BSM community, we have to study in our favorite models really precisely what are the predictions for these rates and the masses in order to study the constraints. And also we have to predict where to look for the additional Higgs states. But we should also not forget that we need something which communicates between experiment and theory. And so we need some accurate and model-independent tools for really studying these constraints and mapping the predictions against the measurements. And this is something that I have been working on in the last couple of years on these two public codes, HiggsBounds and HiggsSignals, but I will be mostly talking in the first third of the talk. Okay, so this is the outline after this introduction. I will tell you a little bit more about these two codes, especially about HiggsSignals, and then I will use these codes to really study the implications for the MSSM. And there I will address two questions. First is what are the possible interpretations of the discovered Higgs boson within the MSSM? And if I have time, I will also ask how light can the light top squark actually be? All right. So the first part, these codes, the main idea is really to provide a public tool for the theory community that they can test their favorite model against the Higgs data. And so the first code here, HiggsBounds, has been on the market for quite a while. It contains only the 95% confidence level exclusion limits from lab Terratron and LHC Higgs searches, because at the time when this code was written, there was no signal, so naturally you can only test against exclusions. There are some extensions of this code, and I will come to this later in the talk a little bit, where we actually have a full likelihood information on how much the model is excluded for certain analyses. And the second code is actually for the purpose that you confront your model against the rate measurements and the mass measurements, and what this code does is perform a chi-square test. And so the advantage for you as a user is that it's just convenient to use them because it comes with all the limits and the observables. You don't have to implement them yourself. It is a validated implementation of those, and it is usually maintained. If there are new results coming up, I will put them into the code and make online or available. And it follows an accurate statistical procedure. And there are also additional checks which are performed whether the searches are applicable to your model or not. So as I said, I will mostly now outline the idea of Higgs signals, because that's what we will mostly use in the rest of the talk. So the idea...
mean whether it's applicable to your model, what do you mean?
So it's in particular for HiggsBounds, where many searches assume that you have a standard model like Higgs, which combines, for instance, different decay modes, and you have a combined limit.
Oh, I see.
And then
checks theoretical assumptions that were
exactly.
made in the interpretation of the analysis.
Exactly.
So this is not actually just comparing your model's events to the events of the search. It's actually somehow using the
It's really just using the exclusion
search.
plot and so on. So
okay.
It's not on the generated event level, but
Okay.
really just compares the rates against the exclusions. Yeah.
Sorry. When you say it only uses exclusion plots, this is what is the standard way to compute the say acceptance? Is it just assuming that it's the same as the standard model?
Yeah. So this is so there is a model assumption there. I will come to this also later.
Okay.
That these efficiencies, at least in HiggsBounds, that the efficiencies of your model for the analysis are roughly the same. So you don't have completely crazy kinematical distributions where the cuts give you completely different efficiencies. In that case, you really have to do the Monte Carlo simulation and test how well this is. Yeah. All right. So the user, so we want to have this as model independent as possible, and that means that the user provides physical quantities, the predictions for physical quantities of the Higgs sector, meaning that for his n-neutral Higgs bosons in the theory, he has to provide the masses, total widths, and the cross-section and branching ratios. So this has to be calculated in advance. These rates actually can be given in some sort of an effective coupling scheme or approximation, and then the code evaluates these cross-sections. And there's also optional input, so you can specify theoretical uncertainties for your predictions on masses and cross-section and branching ratios, and this will be taken into account in the chi-square testing. Then the code uses this information and calculates the signal rates for all these observables. So this is just the signal rate you expect in the model, normalized to the standard model signal rate. And here these efficiency factors are here. And per default, in this case, this is assumed to be equal than in the standard model, but in principle you can also provide different efficiencies. So there's an interface where you can feed them in, but then you have to really do the Monte Carlo generation and study this for each observable, how much is changed. This is quite tedious. Okay, and then the last step, it just performs this chi-square test. And as I said, through this framework we try to cover as many models as possible, so it's a model-independent implementation. The only model assumption here is just that we can factorize these cross-section and branch ratio through the neighborhoods approximation. And we try to be as precise as possible. So what does that mean? For the implementation of the experimental results, we really make use of the signal efficiencies if they are given in a transparent way. So this is a nice example from Atlas, where for the Higgs to gamma-gamma mode, where for all these categories there's this plot indicates how much your signal is composed of which production mode. And this information can be used to infer these epsilons. Okay, and this I mentioned already, that you can specify model-specific efficiencies. And then secondly, so the second part of the precision is in this chi-square evaluation, where we have this covariance matrix here, and we try to include as many correlations as possible of major systematic uncertainties. For instance, we treat the luminosity uncertainty in each experiment as fully correlated. We have theoretical rate uncertainties, which are treated as fully correlated. So if you predict gluon fusion to be larger than it actually is, then you predict it everywhere larger than it is. And also other systematic uncertainties from the experiment, if these are given in a transparent way by the experiment, which is often not the case, unfortunately.
So I guess I don't know what you mean by the standard model efficiency. If the search is a search for some new Higgs state, then what do you mean by what efficiency is being used in this? What efficiency is being used? Now, obviously, the experimentalists made some assumption for the model that they did,
Right.
but specifying that you need more information than saying just the standard model. So you really must mean just whatever assumptions they made.
Right. Well, it's basically the assumption that this is an elementary scalar CP even Higgs, for instance, if this is the analysis is really specific to the CP.
But this is also for additional Higgs bosons, not just right.
Yeah.
So you have to say what properties you assumed about them. Even the mass, presumably efficiency depends on the mass of those.
Sure. So if I say this, if I quote the efficiencies, then I compare to the standard model Higgs at that mass.
Okay, but if it's a charged Higgs, I mean.
Well, okay, so here I'm talking
or...
about Higgs signals, and we only have a signal in the neutral. So all this at the moment does is to compare to the observed Higgs.
So the other one is bounds.
Yeah, sorry.
No, that makes sense. I'm sorry. That makes total sense.
But
I got it.
So on that note, it is actually also possible to include hypothetical signals in this code. So if you want to include the 750 GeV excess in this model, you can. Just put in the observable and you can fit it. Okay, and so we did lots of validation checks, and this is one of the most general one we ever did, was to use CMS data and perform the 6-dimensional kappa fit. And the blue lines here are the official CMS results, and this is our reconstruction. So this was quite a nice agreement we found. So we are quite confident that this whole machinery works. Just to give you an impression of how many observables are currently included in this code, of course I don't expect you to read all this, but these are in total 85 rate measurements, and we have 4 mass measurements from Atlas CMS and gamma-gamma and ZZ channel. Okay, let's move on and study some physics with it. So certainly you know the idea of supersymmetry, so it's a hypothetical space-time symmetry relating fermions and bosons, and if you supersymmetrize the standard model, then you introduce a superpartner for each standard model field, which just differs in spin by 1/2. In addition, you have a second Higgs doublet in order to give mass to up and down type fermions. We know that supersymmetry cannot be exact because we haven't seen any of these superpartners which would have the same mass than in the standard model if this was exact. So we expect there must be some SUSY breaking mechanism, and we roughly expect the SUSY mass to be at the TeV scale in order to still give some acceptable solution to the hierarchy problem. a little bit more details about the Higgs sector. So we have these two complex Higgs doublets, giving in total 8 degrees of freedom. 3 of them go to the W and Z bosons, so we end up with 5 physical Higgs states. And in the real MSSM, which I will be talking about in this talk, we have the first two here are CP even Higgs bosons, this is CP odd, and the charge Higgs. And at tree level, we can specify this the Higgs sector in terms of 2 parameters. MA, which is just the mass of the superscalar Higgs, and tan beta, which is the ratio of the vacuum expectation values. And then we can calculate the masses at tree level. And, we find this well-known result that the light Higgs cannot be larger than the Z mass. So this would be a problem if the light Higgs actually is the standard model-like Higgs that we found. Fortunately, there are very large radiative corrections, especially from the top and stop sector, which can lift the Higgs mass up to around 135 GeV if you still require this SUSY mass scale to be at the TeV scale. So you can actually take this as a selling point if you want for the MSSM, that it actually predicts a light Higgs with around this mass region where we found the light Higgs. Okay, so now we can explain how to get the right mass, but how do we get the standard model-like behavior of this Higgs boson? And this is called the alignment limit, which is just one of the Higgs bosons becomes standard model-like if it is lying in the same direction in field space as the neutral Higgs graph. And this can most easily be seen in the 2 Higgs doublet model, where you choose the Higgs spaces. This is just quantified by only one Higgs field acquiring a VAF, and the other one has no VAF. And if you write down the potential and derive the square mass matrix, then you can study this and see when actually this alignment occurs. And that essentially only happens if this mass matrix becomes diagonal. So you can question when does this actually happen. So in the first case, if this matrix element becomes very large, then you approximately have a diagonal mass matrix, just like in the seesaw mechanism. And this is called the alignment through decoupling limit, or just decoupling limit, and this is where MA is just much larger than all the other terms here in this matrix. But there's a second possibility, and that is simply when the off-diagonal piece goes to 0. And if that happens, so this is called alignment without decoupling, if that happens, this is completely independent of MA. So you can have a light superscalar Higgs still, and in addition you have a standard model-like neutral Higgs. And in fact, it can even happen that this term here is larger than this, which would mean that your heavy Higgs boson is the standard model-like one. And so recently there has been also a study by Jack Gunning and Harry Haber and people where they explored both possibilities within the 2 Higgs doublet model. And now I would like to make the connection to the MSSM and see when this actually happens, the second case here in the MSSM. So first thing to note is that these Z parameters are all functions of the MSSM parameters, and if we calculate the leading terms at one loop to this Z6 term, this off-diagonal piece, and we derive this quite lengthy expression. So this is the tree-level piece, and this is just the contributions from the top and stop sector. And so this we want to set to 0 to get into the alignment limit. And if we do that, we can derive at an approximate one-loop alignment condition, which is given here in this form, where we assume tan beta to be larger than 1 charging number. So I will say a little bit more about this equation on the next slide. It is fair to notice that this alignment in the MSSM is really just an accidental cancellation of one loop and tree level effects. And there's no symmetry reason why this should be happening. It's just a coincidence in the parameter space. So let's look at this equation again. So if you just put in some normal standard values for these parameters, mu, a, t, and s, and so on, then you end up with a 10 beta value, which is much too large to be phenomenologically viable. So you want to have the 10 beta value as low as possible in order to obtain a standard model like Higgs. And this can only be done by really cranking up this mu times at over ms squared. So you make the denominator large and you lower 10 beta. Also, one has to notice that you need a positive value of 10 beta, so the denominator also has to be positive, which is giving you this condition on these parameters. So this was all studied in this paper here, so I'm just following this closely. And what they also did is to propose a benchmark scenario where this alignment actually appears. And so this is just the M8 and beta plane of this benchmark scenario. Just look at the red curves here. So the dotted lines give you the deviations in the signal strength of this general gluon fusion production and Higgs-2 vector boson decay. So 1.2 means 20% larger than in the standard model, 0.8, 20% less. So there's an imaginary line here somewhere where you actually get the standard model like exactly the rate as in the standard model. And this is completely independent then of the MA value. So they also pointed out that there are complementary constraints from searches in the tau-tau channel for the heavier Higgs states. And this is what is shaded here in this plot. So all this region here, up here, is ruled out by these constraints. And so if you put these things together, say you have maybe a 20% deviation allowed in the signal rates, then you end up with a lower mass limit on this pseudoscalar, maybe at around 350, depending on whether you take this seriously or not. Okay, I will use a few more words about these constraints from tau-tau searches. So there was recently CMS published their results in the standard way, meaning that in some certain benchmark scenarios for the MSSM, which is fine, but also not very useful if you want to apply these limits to other scenarios. So what they also did is to provide an exclusion likelihood for a single resonance toy model, which is just given by 3 parameters, so the mass and the rate in the gluon fusion production channel and in the dB bar annihilation production channel, because this search has additional v-text sensitive to both. And so this is here an example for this toy model for 300 GeV for the 1 and 2 sigma regions. But what they actually did is for every point in this parameter space give the likelihood value of how much it is excluded. So it turns out that this toy model can be mapped onto extended Higgs sectors to quite a good approximation by following a very simple algorithm. Just by looking through your neutral Higgs bosons in your model, seeing which ones lie close to each other in mass, and if they overlap within 20% of their mass, then you say, okay, this analysis cannot resolve this. You add their signal rates, and by forming all these combinations, you then have to determine for which one do I expect the strongest exclusion. So you evaluate the expected exclusion likelihood, and then you take that single combination and derive the observed exclusion likelihood value. So we implemented this in HiggsBounds, and now you have really a tool where you can derive a likelihood for the exclusion in this channel for arbitrary models. So what the first thing we did is just to reproduce this this exclusion in this benchmark scenario. So this is shown here. This green line is the official CMS exclusion, and this is our reproduction here. So this worked quite nicely, and in color you see now this likelihood value for the exclusion. And just for fun, we applied it also to this alignment scenario, which I talked about earlier, and we could improve a little bit the implementation of the author's result here. And actually, we derived this slightly more stringent limit here. But this is just to show the applicability of this implementation. So we will use this likelihood now in what's coming next. So now this is a project which we work on at the moment, so all the results are preliminary. We are performing a global fit in the phenomenological low energy MSSM. And so the motivation for this is the question whether all these three possible interpretations, meaning the light Higgs at 125 in the decoupling limit, in the alignment limit without decoupling, or even having the heavy Higgs at 125 GeV as the standard model like Higgs, whether these three interpretations actually survive all the combined constraints from Higgs mass, signal rates, the limits from Higgs searches, from SUSY searches, and from low energy observables. And you can also ask the question, can any of these interpretations actually give a better fit or better description than the standard model? And of course you're interested in what parameter regions are preferred by all these observables and what are the predictions for future LHC searches. A few more technical things here. So we scan 8 parameters, just a random scan. We choose these 3-level parameters, of course, the Higgs mixing parameter mu, the common third generation squark mass, third generation lepton mass, the common first and second generation lepton mass, and chargino mass and AT. And we use these tools to evaluate these MSM predictions. Then we evaluate for each of these points the total chi-square by using the Higgs mass with a theoretical uncertainty of 3 GeV, the chi-square from the signal rates, which is provided by Higgs signals. And as low energy observables, we include 3 B decays, so B to S gamma, BS to mu, B to tau nu, which are all very sensitive to new physics effects. We also include the anomalous magnetic moment of the muon and the mass of the W. And lastly, we include these likelihoods for exclusion from the stau channel, and from lab searches we also have this information in HiggsBounds. And then we have some additional constraints as hard cuts applied from Higgs searches. Here this 95% confidence level limits, and then we also test the most favorable points against the LHC searches in the SUSY analyses, where we generate events with Herbig and process them with this called checkmate, which just checks all these analysis from Atlas and CMS and says if your model is excluded or not. And we have a neutral LSP. Okay, these are results. So this table gives you the chi-square outcome for the standard model, for the best fit in this light Higgs interpretation, and for the heavy Higgs interpretation. For the full fit, meaning all observables are included for the set if we leave out the anomalous magnetic moment of the muon, and if we leave out all the low energy observables just fitting to the Higgs data. And if we start looking at this, we see that the chi-square here is really comparable in all three cases. If we just take the Higgs data into account, if we add the other low energy observables, except for G-2, then still we end up with very comparable chi-squares. In fact, in both these cases, the standard model gives you the best p-value because it has less parameters. So it has a larger number of degrees of freedom. But once we, of course, include also the G-2 observable, the standard model is well known to be in discrepancy with the observations by around 3 sigma or maybe before. So this receives a huge penalty here, while both MSSM predictions can still give you an explanation of this observable. Here, just for reference, I also give the parameter values of these best fit points. You can already see that the light Higgs here is found in the decoupling limit and has relatively small lepton masses and chargino masses. This is just to give a sizable contribution to G-2. And for the heavy Higgs, well, I will show you some more results on the parameter space in a moment, but you can already notice that the mu value is extremely large here.
Did anybody ever estimate the tuning in one of these, sort of, I don't know, what do you call it, the wrong Higgs scenario or whatever, the one where the heavy 125 GeV is the heavy Higgs? Must be fantastically fine-tuned.
That's true, yeah.
I mean, it's fair, it's totally fine to do the phenomenology, I just wondered.
Yeah, and in particular,
you're tuning a lot more stuff to be light and so on, right?
Yeah, well, I mean, it's also your personal opinion whether or not you find fine-tuning as a
right, but I just mean
argument
the
or anything. But
sensitivity, like just take some normal definition that people use. You could argue with it, but just what is it? It must be.
It is certainly very fine-tuned.
Especially with a huge value of mu.
In particular, I would rather worry about vacuum stability in these cases, which we didn't check explicitly. So, yeah, this is still open for discussion. So, we show you.
When I was a kid, that was the motivation for supersymmetry.
Yeah.
Now it's just studied for its own sake, I guess.
Well, I wouldn't reject models just based on fine-tuning arguments personally. But, so I will show you some more results in the light Higgs case and then turn to the heavy Higgs case. So just looking at the Higgs rates here, so these R values are just idealized signal strengths in these decay modes. You see that all are basically around 1, which is the standard model prediction. You might see some slight enhancement in the gamma-gamma mode, but not very significant. There are basically two ways to get this enhancement. One is just by suppressing the Higgs to BB bar mode, which would enhance all the other decay modes, and also through light staus, where you can get a direct contribution to the partial roots of the Higgs to gamma-gamma. So let me show you, explain you a little bit this color coding. So all these blue points are just allowed by Higgs bounds and checkmate, so they pass the exclusion limits. And in red and yellow, we indicate the most favorable points from the chi-square. Okay, so let's have a look at this M8 and beta plane. You see that most of the points are really found in the coupling limit. It's not very surprising. But also you see that some of these points survive to MA values down to 200 GeV. And if we have a closer look at those points and plot this quantity which was here in the denominator, mu times AT over ms squared, then we see actually it has very sizable values of this quantity. So, yeah, and this quantity actually has to be positive. All right, so what does this also imply for the stop sector? If we look at in this plane for the stop mixing parameter versus the light stop mass, we see that we still find kind of, so the 2 sigma points we still find at around 300 GeV stop masses if we really go to this maximal stop mixing case. And note that we also assume this universality in the 3rd generation squark masses. So if you split this up, and you can even have lower stop masses. I will come to this in the last part of the talk, actually. So, yeah, as I said, these parameters are positive. Actually, I didn't say it, but okay. So this alignment region here, if we just look at the low MA points, we find only in this positive XT branch, and this is just because the mu value has to be positive due to these low energy observables G-2 Peters gamma. Okay, a few results on this heavy Higgs interpretation. It is a very narrow and limited parameter region here, where MA is between 150 and maybe 165 GeV. So what happens here at this edge, there's a very sharp edge at 150 GeV here, and that has to do that Higgs signals takes the pseudoscalar Higgs into account in the tau mode, because the tau mode is has a very poor mass resolution. So if this Higgs gets too close to 125 GeV, then it overlaps with the signal, and then you get a too high rate, the tau final state. And that's why we observe this kind of sharp edge here. Again, I already said we observe these solutions only for very large mu values. In fact, it should also show up in this region here, and I think we're still investigating this. There's some numerical instabilities happening up there.
Sorry, are you telling me, in the back on the last slide, you're telling me that if you just blindly do a fit to the MSSM Higgs sector, assuming that the 125 GeV state is the light scalar, this is what you get? Sorry.
No, this is for the heavy Higgs.
And heavy Higgs.
Yeah.
Sorry. I'm sorry. Okay. Yeah, I understand now. Thank you.
Okay, and so you might consider this being ruled out by vacuum stability considerations, power fine-tuning, depending on your taste. What we find also is that the light stop has to be in this rather narrow mass window here, but this, I mean, if you extend the parameter ranges of your fit towards larger values, that might actually give you also larger stop masses.
So yeah, in fact, you're like, why do you get a light stop? I mean, what is the...
So one of the reasons I suspect is if you go back to there, you want this matrix element to be smaller than this. Okay?
Okay.
Because this should be the heavy Higgs,
Yeah.
this standard model light. And MA is already 150 GeV or so. So that means that this has to be negative. And if you study this expression of Z5V squared, there's a log piece of MS over MS squared over MT squared, and then there's additional terms. And the additional terms give you the negative contributions, but the log piece only gives you positive contributions. So I guess if you have too large MS, then you end up with a positive Z5 and you cannot get this down. All right, so the question which is most interesting in the heavy Higgs interpretation is where are the other Higgs states? And so we find that the light Higgs has typically a mass around 60 to 100 GeV and has extremely reduced couplings to the vector bosons. This is also one of the explanations why this hasn't been seen or excluded by the lab experiment. Also, you have a light charged Higgs, well, relatively light, I have to say, because it sits more or less directly at this threshold to the top quark. So the usual way you look for these light charged Higgs is in the top quark decay, but in this case it is kinematically suppressed. And actually you see here this is the exclusion limit from these charged Higgs searches, and it only goes to 160 GeV here. And additionally, you have for some of these points you have this charged Higgs to tau mu decay suppressed by a competing decay, which comes up here in this particular case, where the charged Higgs decays into the light Higgs and the W boson. And I think this is a signature no one ever has thought about, at least not in the context of the MSSM. So it might be a way to probe this scenario. Okay. For the rest of the talk, I would like to tell you a little bit about this question of how light the light stop can be. And this is work with Stefan Liebler and Stefan Kumo, which we recently published. So the motivation is sort of given by the case of electroweak baryogenesis in the MSSM, where you need a very light stop in order to get a strongly enough first order phase transition, which leads to out of equilibrium regions during the electroweak breaking phase. So this is one of the Sakharov conditions you need for successful baryogenesis. The question is just how light this stop actually has to be, and it is kind of a tricky question, and I don't really feel very qualified to judge on this question, but one way to probe this question is by doing perturbative calculations of this finite temperature effective field theory, effective potential field theory, and so many groups have performed these studies, and for instance this paper quotes that the stop mass has to be at most 110 to 120 GeV. But also it is known that in this finite temperature field theory you encounter infrared divergences, which really require non-perturbative calculation of the phase transition. And there's one group that performs a lattice study of this, and they actually demonstrated that you can even get a strongly enough first order phase transition if you have stop masses of that order. So now we just want to study this. So this just take as a motivation to probe these low stop masses, and of course to derive limits from the LHC you can either look directly for light stop pair production, or you can infer constraints from the Higgs data, and this is what we will follow here. So of course I told you just a few slides ago that we need stop masses of at least 300 GeV, but there we really assumed that the left-handed and right-handed squark masses are the same. So in order to really get down to these low stop masses, we have to accept here that there is a mass splitting in the stop sector. So you have so these are the radiative corrections to the Higgs mass, and in order to get 125 GeV Higgs, you have to have an S of the order of a TeV. So you can achieve this by just making this as multi-TeV, and then you can get low to very low values of the right-handed stop mass. At the same time, you will also obtain very small stop mixing, which is just governed by this expression. If this is very large, this goes to 0. And this has important implications for the Higgs phenomenology, because in this case, if you have a very light stop, you get a huge enhancement of the gluon fusion cross-section, where the stop is just running in the loop, and in the zero mixing case, you just get a positive contribution. So this looks like it's highly in conflict with the Higgs data. At the same time, by the way, you also get the same contributions to the Higgs to gluon decay, and it also affects directly the Higgs to gamma gamma mode, but there it gives a negative contribution, so this rate actually goes down. So we want to use these features to really derive lower mass limits on the stuff. And again, we just look at the signal rates here because we argue that you can just tune this decoupled SUSY scale to obtain the correct Higgs mass.
Sorry, because I know you're not talking about it, but can you just remind me or tell me, so a stop that low, how does it decay? And is that not already ruled out by direct searches? Can you just
there are direct searches. I have a backup slide for this, but it is basically the message is that it's still model dependent in the way that you assume certain decay mode. So for instance, to charm neutralino, or you can have 3-body or 4-body decays through virtual top or virtual W. And depending on really the mass hierarchy, there are still gaps. I can actually show you this plot maybe.
I'm sorry.
So these are the constraints if you have a pure decay to charm neutralino, and there you basically rule out all this interesting mass regions. So these are very strong. But in this case, so this summary plot is from this paper here. There is still, so there are different searches that try to probe this, so mono-jab, one left and two left-hand searches, and there is still a gap here down here, which is not ruled out.
So what's being assumed in this model? How does this stop decaying?
The stop is decaying to, like, okay, in this case, I think it
the model that's allowed. What's in that allowed region? What is the stop decaying to?
In this allowed region, it decays into 3 fermions and wait a second. And a B jet. So it's basically stop decaying to virtual top B, and the virtual top decays to virtual W and B.
The claim is you can make that dominate over sharp neutralino.
Yeah, it's possible. I mean, this is CKM suppressed, and I think the chargino plays a role in that loop as well. So if you decouple the charginos, then this is dominating.
Okay, thank you.
It's really model dependent in some sense. So in this paper, actually, they argued that if you additionally require more beat jets or beat tagging, then you can close this window. But as to my knowledge, this hasn't been done experimentally yet.
Thank you.
Okay. So where we are. Okay. So what we did is to consider several scenarios here. The first 3 where we go to the decoupling limit and just consider a light stop, or we also add the light stau and the light chargino because those can directly affect also the Higgs to gamma gamma partial widths, and then they might weaken this tension with the Higgs data a little bit. And in the 4th case, we consider also non-decoupling effects. And in these first 3 scenarios, we allow also for a generic Higgs to new physics decay mode. In the MSSM, this could be something like Higgs to neutralinos, which would give you an invisible final state if R parity is conserved. Or you can think about some beyond the standard, beyond the MSSM decays. So we are pretty agnostic about this. But what this does is that it overall suppresses all your decay rates to standard model final states, and thus can partially compensate the enhancement in the production cross-section. And so you play that game to derive sort of standard model-like couplings. It is standard model-like signal rates. Okay. So just for reference here, I gave the current limit for Higgs to invisible, which is currently at 28%. So the first scenario, where we just have a light stop and the rest is just decoupled. So this plot shows you 1 and 2 sigma regions in this light stop mass branch ratio Higgs to new physics plane. And so if you just look at this, you already see that you can have maybe at this point light stop masses of 144 GeV, but only if you add this additional branch ratio to new physics. The contour lines give you an impression of how the signal rates behave. So for instance, this first one is gluon fusion, Higgs production, and then decay to vector bosons. And as I said, if you go to lighter and lighter stop masses, the rate goes up. So in order to stay on the standard model signal strength here, you also have to increase the new physics decay mode. So you suppress the decay rates to standard model to this final state. Okay, I also have, yeah?
Sorry, can I just ask, so is it true that roughly I can think of this as you're assuming that this is constrained, is it correct that this constraint is mainly coming from the Higgs-gluon coupling, and you're assuming that there's no additional new physics other than the light stop in that? Right. So I could roughly think of this as saying, this is a bound on the light stop contribution to the Higgs-gluon coupling.
Yes.
But you're being very agnostic, and so you're allowing
yes.
this other
yes. And you arrive at this constraint just by the splitting of those signal channels which are initiated by gluon fusion versus those from vector boson fusion or VH production, right. Because those are really not affected by the stop, by the light stop. Right. So this is also seen by these red lines here. If you just increase this branching ratio, then you just suppress more and more this rate, and eventually the splitting gets too large, so you can derive this constraint from these data. And actually, so in this particular case, there's also a splitting from the gamma-gamma mode, where the stop has also its contributions. So in this case, it gives a negative contribution to gamma-gamma, so this is very, very tiny. And this makes the fit even worse. So this is just a motivation why we want to introduce maybe other light charged states, because they can give a positive contribution to the gamma-gamma again, maybe weaken a little bit this tension. And this is just what I showed you next. So if you add a light stau, the contribution to a Higgs to gamma-gamma is particularly large if we have large mu 10 beta. There are additional constraints which we took into account from vacuum metastability. So if this is too large, then we encounter those problems. We use some Oxford formula and so on. But assuming that we fulfill all these constraints, we can look at these green and yellow dots again. You see again this effect that the gamma-gamma rate decreases with light stop masses, but also that due to the influence of the light staus, we can now also increase this again. So you see that before we had this limit around here, we can now, due to the influence of the staus, lower this lower limit on the stop mass and derive at some value of around 123 GeV. Okay, and you can play the same game for the chargino, and the limit is basically also in the same ballpark. Here, by the way, this contribution to gamma-gamma is maximized for low mu 10 beta, because it's proportional, or it is large for large Wiener Higgs mixing. So what we assumed here in the scan is also that mu is equal to n2. And lastly, we thought about, well, what if you have, instead of this new physics decay mode, you can suppress the rates into the well-measured final states by just increasing the decay rates to dB bar and tau, which are not so well measured. So you can, partially compensate again this enhancement of the cross section. And we performed this fit by allowing A to be small, where you can have these non-decoupling effects, so you can have enhancement the down-type fermion Higgs couplings, and we again find a similar mass limit here in this case. You might also think that at least from the green points you have some slight preference for lower and A, but this is not really significant.
Why don't you get the same thing from large tan beta, don't you?
Yeah, but you have to be away from the decoupling limit, right?
Sorry.
I mean, tan beta plays definitely a role here, because if you increase tan beta, you increase those couplings.
Right.
But if you're in the full decoupling limit, it is basically independent of tan beta. And of course,
Sure.
yeah.
Sure. Okay. I mean, but we're not that close to the decoupling.
No.
Okay. Anyway.
And it doesn't have to be huge. These things. Okay. Just a curious thing about this scenario is that we saw that there's a nice new signature which might or might not be useful, where you produce a heavy CP even Higgs, and it can actually decay to the light stars. Of course, I don't know if this is really promising, because you can also directly produce the stops, but we found it interesting.
There's a paper by John Tillich from some time ago where it talks about Z prime production of superpartners, and you can really make a lot of use if you have a narrow resonance. That's actually incredibly useful. It's kind of like being a E plus E minus collider again, right?
Mm-hmm.
Because you know the center of mass frame, and so you can do a lot of the stuff that E plus E minus people do. So it certainly would be worth seeing.
What mass ranges did they consider?
So I think he was considering a much, this was in the heady days before the LHC actually turned on.
Okay.
And so he was considering a very optimistic scenario with a very heavy Z prime, very hard events. So it was a very completely different regime, but I just mean, you may want to look at the paper for inspiration. You might see something that may be useful.
Yep. All right. So this is my summary. In the beginning, I told you about these two codes, HiggsBounds and HiggsSignals, which you can use to test your favorite model against the Higgs data. You can check it out on this website, and I'm happy to assist with any installation or usage of these codes. And then I looked at these three possible interpretations of the MSSM: the light Higgs in the decoupling limit, the light Higgs in the alignment without decoupling limit, and this heavy Higgs interpretation. And at least from a phenomenological point of view, they all provide good agreement with the Higgs data and low energy observables. Of course, in these two cases, you might worry about these parameter choices, so you have to have very large mu-at parameters, which might be worrisome. And in the last part of the talk, I showed you that you can actually get light stop masses in the range of 120 GeV by accepting that you have a large splitting in the stop sector, and that you also allow for light charged states like staus and charginos, which can affect the gamma-gamma rate. And so this might leave a small window for successful electroweak baryogenesis in